Hello viewers, I am Dr. KSR Radhika, working as Associate Professor in the Department of Computer Science and Engineering, SRKR Engineering College, Bhimvaram, Andhra Pradesh. In this session, I am going to explain about the task and its data. So the objectives of today's session are to know about the task and its data and to explore the shared data of tasks and also to understand the reentrancy. First of all, we will look about the task and its data. So a task has its own private data. So private data, we have its own register values, program counter, and stack. So if you see in this example, so here we have three different tasks. So each task has its own separate registers and also the stack. So similarly, the task 2 has, these are the register values, and this is the stack data. And similarly, task 3 also have the register data and also the stack data. And also it has the other data. So other data means you can have some global data or static data or uninitialized data, initialized data. All these comes under the other data. So all the other data are given here. So that means what? The other data can be shared by other tasks. So that means if you see here, the task 1, 2 and 3, all the three can share this other data. So this data can be shared by different tasks. So RTOS maintains its own private data structures which are not available to any other task. So if you observe here, so RTOS, it maintains its own data structures. So these are not available to any of these tasks. So that is task 1, task 2, task 3. So it cannot access these RTOS data structures. So these are private to only the RTOS. So the tasks in RTOS, if you consider the tasks in RTOS, so they are simply like threads, then like a process. So you can consider them like threads. So this is how each and every task, that is the task and the data in the RTOS, that is in the real-time operating system. So now we will see how the data is shared between the different RTOS tasks. So this is the example that we have already seen in many of our sessions, that is underground tank monitoring system. So we have seen this example in the previous session also. So this is the same example where we have two different tasks. One is we respond to button task and another one is we calculate tank levels task. So here we calculate tank level task is, it calculates the tank level. It calculates the tank level at some time. So that means at some intervals of time, it will be calculating the tank level. So if you observe here, so while loop, so this is a continuous loop, read levels of float in tank I. So here you are measuring, so here you will have more number of tanks and you are measuring the float level in tank I. So and after measuring the float level, you will be doing certain calculations of your tank level. So after that calculations, what you have to do, you have to store the data in some variable. So here we are storing the data in tank data of I. So here tank data of I, it is a structure. If you see here, it is a structure. So structure which has two parameters, that is it has tank level and also the time updated. So it has two parameters. At what time you have taken the tank level. So depending upon the time, so the tank level may be different at different time intervals. So that's why, so here we have two different parameters in this tank data. So, and you have the maximum tanks. So how many tanks you have, that many number of this max tanks specifies the number of tanks in your underground tank monitoring system. So here tank data of I means, that means you are measuring the tank level in the ith tank. So that's why here we have given it as tank data of I dot I time updated. So that is the current time. So at what time you are measuring, you have measured this particular tank level. That time is saved in this time updated. And similarly, tank data of I dot tank level is, so the result of this calculation, that is already we have read the float level and we have done the calculation, and the result of this calculation is stored in the tank data I dot tank level. So here we are saving the tank level and here we are saving the time, that is the measurement time, at what time we have taken this tank level. So next you can do some another work that is related to that one. So, and this is another task, we respond to button task. So this is a task, whenever the user presses a button, then this task will be executed. So here whenever the user presses the button, so here the user wants what is the tank level and what is the time updated. Suppose if you consider it like that. So that means what, here just we are printing whatever time and tank level we have read here, those two are being printed here. So with this printf. So that is with printf, we are printing the tank data I of time updated and tank data I of tank level. So these two are being printed here, that is time and the level. So these two are printed. So that means what, here the tank data is the variable that is shared by both the tasks, that is we respond to button task and we calculate tank level. So it is being shared by these two tasks. So here in these two tasks, this task is given the low priority and this we respond to button task is given high priority, because immediately this will be in blocked state. Immediately the user presses the button, it will be unblocked and then it has to print the that particular tank level. So this is what it has to be done in this task. So what happens here? So here it should respond immediately to the user. So that's why this is given high priority and this is given low priority. So for example, suppose if the processor is executing this particular task. So whenever it is executing this particular task, so for example, previously at time T1, it has updated these two values. At time T1, the time is T1 and the tank level is L1. For example, consider that those are the previous two values. Now again it is calculating the tank levels. So that is at time T2. So at time T2, again the level will be L2, isn't it? But what happens is, suppose, so already we have measured at time T1. The time is T1 and the level is L1. Now at time 2, we want to measure again the tank level. So we have measured the tank level and we have done the calculation and then we have updated the time also. So the time we have updated to T2. So we have updated the time to T2. So before it is how much? It is T1. So that time has been updated to now, because it is T2, it has been updated to T2. But immediately after this statement, suppose if the user presses the button immediately after this statement. So then what happens? Because this is of low priority task, so this task will be suspended and it goes to ready state and immediately the control will given to this high priority task. So that means what happens? So in this tank data I, time updated is T2, but this is not yet updated. So this is L1, that is the previous value. So but what happens? Immediately after this statement, the button has been pressed. So that's why the control from here, it goes to this high priority task and it will print the values of that are available in the tank data I. So here in the tank data I, this value is, that is time updated is T2, but tank level is L1, which are wrong values. So that means what? So here because of sharing the data between the RTOS tasks. So you got the problem of shared data. So that means what? So either you should, this task should be called before these two statements or after these two statements. So then only you will get the correct value. So if it is called before these statements means, so you will get both the previous values, that is T1 and L1. If you call, if this task is called after the these two statements means, then what happens? It will be T2 and L2. So this is the problem of whenever you are using some shared data between the RTOS tasks. So you have to solve this problem of shared data. So whenever you are writing the code, how the code fails. So why it fails? Because of the shared data problem. So this is a simple C code. Why it fails? So for example, if you take here, we have two tasks. One is task 1 and another one is task 2. And you have one static int C errors. C errors is a variable that can be it is a static variable. Okay, so here what happens, you are writing one more function, so that is we count errors. So int C new errors, so we are giving a new value and that value is being updated to the static variable C errors. So static variables means what? Once it has been created, it will be alive throughout your program and it will be destroyed only after the closing of your, that is before the closing of your program. So now what happens, suppose if this function is called, so whenever if you see this function whenever it is converted to assembly code, so it will be written to this many number of instructions. So simply here by seeing in high level language, it represents like a single statement. But once it is written in assembly code, so it will be written to this many number of statements. So first this C errors plus is equal to C new errors. This single statement will be converted to this many number of statements. So first what we are doing, we are moving C errors to R1. Then we are adding C new errors. So whatever new value we have passed here, that value will be added to this R1. R1 contains what? C errors. So these two will be added and that will be stored in R1. And next what we are doing, we are moving the R1 to C errors. So that means what, here a single statement is written in assembly code as three statements. Suppose if you have this function, suppose if you call, suppose if this is the order that is being executed. So for example, suppose if you call task 1 once and task 2 once, then what happens? So in this one we are calling once and in this one we are calling once, this function. So suppose initially its value is 5. So that means what? So the 5 value, when added this 9, it becomes 14. And afterwards task 2 is called. So that means what? Already it is 5 plus 9, that is 14. 14 plus, now again the new error value is 11. So 14 plus 11 means it is 25. But instead of 25, see how you will get the wrong value. So for example, task 1. So now first task 1 calls this function with 9 value. So then what happens? For example, suppose it is executing these statements. So these two statements are executed. So that means move CRS to R1. So that means what? R1 will be 5 because the initial value of CRS is 5. Assume it like that. So R1 is equal to 5. Next, R1 is equal to R1 plus C new errors. That is R1 is 5. 5 plus 9. This is new value. That is 5 plus 9. Now it is R1 is equal to, it is 14. So after these two statements, suppose now RTOS switches to task 2. So again, now it has been switched to task 2. Again, what happens? Again, it starts from the beginning of the task 2. So again, move R1, CRS. So you have read the value of CRS to R1 in task 1, but you have not updated that value. So that then what happens? So then what happens? So now in CRS, so it is 5. So 5, it has been added 9 and it has become 14. But this value has not yet updated. It has not been updated. So that's why once this task2 function is called after these two statements, so then what happens? Again, the same 5 will be given for task2. So that's why what happens? Again, R1 will become 5, that is 5. And then it will add this new value 11, that is 5 plus 11, it becomes 16. And this 16 again, it has been written to CRS. So, okay, now it is 16. So after writing this value 16, now this task 2 has been completed. Once it is completed, because task 1 is not yet completed, one more statement is there, that is this one. So now what happens? Again, the control switches, that is the RTOS switches to task 1. So again, it switches to task 1. So then what happens? So before it is 16, but now this 16 value, so here R1, what is the value? It is 14. So this 14 value is overwritten onto 16. So then what happens? This is the 16 value is overridden by this 14. So finally it gives the answer how much? 14, which is wrong value. So you should get the answer, correct answer is 25, because both the functions are called. So 5 plus 9 plus 11, it should be 25. But instead of 25, so you got how much? Only 14. So in the intermediate, you got 16, but that value has been overridden by 14. So anyway, this 16 is also wrong value and this 14 is also wrong value. So this is how the code will fail whenever you have the shared data between different tasks. So this is the problem of shared data whenever you are using the data between different tasks. So whenever you are using different storage variables, then also you have the problem. That is, whenever you are using the storage variables, so suppose if the variables are stored on memory. So for example, if you consider C language, so in C language, so some of the variables are stored on fixed location of your memory, and some of the variables are stored on stack. So depending upon the variables where they are stored, so if they are stored as private data, that is on its stack, so then we don't have the problem. Suppose if they are stored on fixed memory location, so then that data can be accessed by other tasks also. So for example, if you take these different variables, so the static int, so this is a variable, this is stored on, it is stored on fixed memory location. Similarly, this is also stored on fixed memory location, just integer, public integer. So this is also normal integer variable, but here you have given just some value. This is uninitialized value and this is initialized value. This is also stored in fixed memory location. This is also stored in fixed memory location. So all these variables are stored on fixed memory location. But suppose if you consider in this function param and asterisk parameter, these two are private to this particular function. So that's why these two variables will be stored on the stack of this function. And also again, static int is also, it is also stored in fixed memory location. And in the case of int local, so this is also local variable to this function. So that's why this variable is also stored on, it is also stored on the stack of your function. So that means only this param, asterisk param ptr and local are stored on the stack of your function. Suppose if the variables are stored in the fixed memory location of in your memory, so then those variables will be shared by other tasks. So that's why whenever you are writing the code, you should be careful that whenever the data is being used by different functions, so you will get the shared data problem. So that's why here we consider the topic reentrancy. So what is meant by reentrancy? So what is meant by reentrancy? Reentrancy, so that means what, here you have observed the problem of shared data. So in order to solve the problem of shared data also, you can use this concept called as reentrancy. So when a function is said to be reentrancy, so reentrant, so a function that can be called by multiple tasks, the function that can be called by multiple tasks and still work correctly. Even if the RTOS switches from one task to another in the middle of execution of a task, then that particular function is called as reentrant function. So that means, suppose if the RTOS switches from one task to another task, even though it is switching also, if it works correctly. So whatever previous functions we have seen, they are not working correctly. Suppose if the RTOS is switching from one task to another. So that's why we are getting the wrong output there. So even though the RTOS switches, if it works correctly and it gives the correct outputs, then we call that particular function as reentrant function. So in order to be a function to be as reentrant, so it has to follow three rules. It has to follow three rules. What are those three rules? The first rule is the function may not use variables in a non-atomic way unless they are stored on stack or its private data. So that means the function should use only the stack data or private data. You can say it as simply as stack data or private data. Then we don't have any problem. So even though if the RTOS switches also, because the data is private, the data cannot be used by any other task. So that's why your function will work correctly. That is the first rule. And the second rule is reentrant function may not call any other functions that are not reentrant. So the reentrant function must not call any other function that are not reentrant. So this is the second rule. It should not call any functions that are not reentrant. And also the third rule is the reentrant function may not use the hardware in a non-atomic way. So it should not use the hardware in a non-atomic way. So these, whenever if you write the function following these three rules, then we can say that that particular function is reentrant. That particular function is reentrant. So that means you can solve the problem of shared data. So that is, if the RTOS switches from one task to another task also, our reentrant function will give the correct output. So that is what is meant by reentrancy. So for example, if you see these examples, why these functions are not reentrant. Suppose if you see this example, first example. So here what we are doing, here we are giving boolean. So this is boolean f errors, which is a global variable, and in this display function you are using the printf to print the j value, and you are assigning some j value, and then you are giving f errors is equal to true, and else here in else also you are printing some value, some code you have written. So you can say this function why it is not reentrant is, so out of those three rules, here it is violating two rules. The first rule is, suppose if you consider this boolean f errors, so this f errors is a variable that will be stored on the fixed location in your memory. So that means what, this variable can be used by other tasks also. So that means what, here it is violate. So already we told that reentrant function should use only the stack data or the private data. So this is not stack data of this particular function, or it is not the private data of this particular function, but it is using this variable. So that's why this variable is stored in a fixed location of your memory. So that's why this may be shared by other tasks. So that's why, because this function, display function, is using this, so this is not reentrant function. That means it is violating the rule 1. It is violating the rule 1. And one more reason is, it is also violating the rule 2. What is the rule 2? A reentrant function should not call any other function which is not reentrant. So suppose if you see in this display function, here you are calling printf function, here and here. So printf function is not reentrant function. So this is a predefined function of C language. So this is not reentrant function. So you are calling this printf function in this display function. So then automatically, if this is not a reentrant function, so automatically you can say that display is also not a reentrant function. So that means what? Here it is violating again the rule 2 also. So that means what? Here this example, it is violating rule 1 and also rule 2. So for example, if you take this example, so here plus plus C errors. So here this is a function where it is using the static int C errors. So the static int C errors is a variable which is stored on, this is also a non-static variable. So this is also stored in fixed location in your memory. So once this function is using the C errors variable, so this is also not a reentrant function because this is violating rule 1. So that's why this function is also not reentrant function. So suppose if you convert this function to assembly language. So that is if it is converted to assembly language. So depending upon the microcontroller, suppose if you take 8081 8-bit microcontroller, this will be converted to this many number of instructions. So this many number of instructions. So suppose if you have this many number of instructions means in between these instructions, suppose if an interrupt occurs, so then what happens? Automatically the RTOS switches from here to some another task. So then what happens? Your function, so it is not atomic. So suppose that is it is not atomic or reentrant. Suppose if you take Intel 80x86, so then it is just specified in only one instruction, that is inc CRS. So that means what? This is only one instruction. So here we can say that it is atomic. So once it is atomic means we can say that it is reentrant. So depending upon the code and also depending upon what processor you are using, so you can write the reentrant functions and you should take care of the shared data problem. So this is how you can handle the shared data problem in the task, between the task of your RTOS in embedded system applications. So if you like my video, please like, share and subscribe to our channel. Thank you.